I first have to thank the conference organizers for giving me the opportunity to speak about this work, which I'm very excited about. So this work was partially funded by NASA Quail back in 2016 and involves collaboration with Los Alamos National Laboratory. So we have two people from LANL here. So one of the problems that's dominated the field of quantum annealing is the question of how does quantum annealing as an optimization algorithm scale with problem size, right? And in this direction, one of the most key points is that is now believed that the annealing time is dominated by what's called these computational bottlenecks, which are points along the annealing trajectory where the gap scales exponentially with problem size. And this occurs when you're trying to anneal to a particularly tough spin glass instance. Okay, so in this work, we consider an analytical approach. So we consider a very simple 1D frustrated spin chain we call the F model. This has one tunable bottleneck property, so it's great to study as a toy model, but it's also frustrated. In particular, the number of anti-ferromagnetic bonds is odd. So in particular, the ground state always frustrates a particular bond. And in particular, this is a non-Hamming symmetric model, so this is not a mean field model. So that's another novel aspect. Okay, so to test the usefulness of the toy model in terms of gaining insight into the behavior of quantum annealing, what we did is we scanned this frustrated spin chain onto the D-Wave 2X at Los Alamos National Laboratory. And according to our analytics, there is a first-order phase transition late in the anneal of this problem in some region. So here, the x-axis is the value of L, and the y-axis is the value of R. And what we do find is that if we run this on the D-Wave 2X, we do get the probability dropping from about 100% in the yellow to close to 35%. So indeed, it seems to be an interesting toy model to investigate these bottlenecks. And also, another thing we can do is we can look at, just basically very simple, master equation simulations of this model on the D-Wave, and we get some qualitatively good agreement with D-Wave results. Okay, so again, what I want to mention is that this model, I believe, represents a new direction in terms of analytically characterizing the computational scaling of quantum annealing as an optimizer. In fact, so this differs from models that have been considered before, which are all-to-all or mean field in nature. So that's exciting to talk about. So, of course, there's no free lunch when you try and add, interesting properties like frustration and breaking translational symmetry. The model becomes particularly hard to solve, especially with realistic longitudinal flux qubit noise, which is non-Fermianizable, and so is particularly hard to characterize. And there are sentences in these foundational works by Lieb, Schultz, Matisse, and also in McCoy and Wu on the two-dimensional Ising model, showing that this is a very difficult open problem in mathematical physics. Okay, so one thing to note, so in this problem, what makes it difficult is partially the frustration. So to solve, the first thing you do to solve a 1+1 dimensional spin glass is you change basis to this fermion algebra of gamma matrices, which anti-commute for I not equal to j and which square to 1. And in particular, what you note is that when you have periodic boundary conditions, the model splits into two distinct free fermion models. And this is representing the fact that the integrability model of the model is kind of at its limit. So to incorporate the effects of frustration, there's this kind of doubling of the Hilbert space that is involved here. And in particular, what we can see is that the way that frustration manifests in this toy model is that there's a parity constraint. Basically, if you look at the odd fermion Hamiltonian, which is H minus, all of the excitations are positive, and because only the odd parity eigenstates are physical, there has to be at least one fermion excitation in the ground state, just because you're in the odd sector. And so what that means is that we get an avoided crossing whenever the energies of two particular bound states cross and one becomes more energy favorable, causing a fermion to have to, in this case, tunnel from left to right in the graph. So that's the basic physics of this this new frustrated 1D model. So again, it's been well known in the field that the non-fermionizable noise is quite difficult to deal with. Again, here these Giuseppe Santoro and others, they mentioned that we should ignore parity subtleties in solving these models because they basically make the problem impossible to solve. Similarly, in this scientific reports paper by Ames and others, even for a uniform icing chain, they resort to calculating everything numerically for realistic noise models. So what I'm going to do right now is I'm going to show how you can circumvent these difficulties with a couple of steps. So what we've done is we've made some progress towards analytically solving a non-fermionizable noise in 1+1 dimensional spin glasses. Okay, so the first thing to note, so now what we're going to do is we're going to get our hands dirty and we're going to deal with the subtleties of these parity-dependent boundary conditions. So in particular, if we have any spin glass Hamiltonian H, there exists a frustration-free version of it, which differs by basically flipping the sign of one of the couplers. Okay, and what we note is that if you flip the sign of one of the couplers, you get something that is not frustrated, because a spin glass in 1+1 dimensions is frustrated if and only if the number of antiferromagnetic bonds is odd. So we have this intertwining relation that allows us to kind of remove frustration or look at a mirror spin chain model that might be easier to tackle. So that's the first thing to notice, is to introduce this this new model that is frustration-free that we'll deal with later. Okay, so one thing that's special about this 1+1 dimensional icing model that we have considered is that if we take one of the defect operators, this C sub r, this is one of these fermion bound states that's localized on the right-hand side of this graph, it passes by this sigma z operator up to exponential corrections in the distance from that coupler. So J sub r is the center of that fermion bound state. And this is, you can derive just by looking at just quantum numbers that you can tabulate, and you can show this relation, which is very, very interesting. So how do we use this to calculate tunneling matrix elements? So let's get to the point. So suppose we want to consider a diagonal transition in our genuine F model. So what we do is we can write out these low energy states in terms of vacua and respective parity sectors. And what we can do, again, if you look up here, this intertwining relation between H and H tilde allows us to change parity, remove frustration at the cost of flipping the parity. Okay, and then what we do, as you can see on the left, we have a fermion bound state. We have an odd fermion number state which has even parity. So that's a false eigenstate. But what we can do is we can then turn this into a genuine matrix element by actually passing that excitation past this non-fermionizable noise operator up to these exponential corrections. And finally, what we can do is, what we notice is that in this particular case, what we get is the off-diagonal matrix element of sigma z in the ground state subspace of a quantum ferromagnet, in particular H tilde. And what we can do with some work is to show that this tunneling matrix element is proportional to n, so it diverges linearly, and it contains a factor of the spontaneous magnetization squared of the uniform icing chain. So this is remarkable in that this is independent of L and R, so basically the defects in the model. And the reason why that is because there is a boundary effect in the model. So if we plot this tunneling form factor right near a bottleneck where we get this magnetization, we can see that the So this horizontal line is 1/2 the spontaneous magnetization squared of the Ising model. So we find this very interesting boundary effect, and this boundary effect is what leads to this noise amplification. And we get the prefactor from this analytically, which is very interesting. Okay, so one thing, after we derived this result, what we did is we looked back at previous papers by Ames, and we found that there they looked at a two-dimensional Ising spin glass with second nearest neighbor interactions. And what they did is they defined this RMS transition matrix element, M sub alpha, and they noted that it converged to some it had some average value. And here, what we can do here is for the F model, we can show that scaling factor is the spontaneous magnetization over square root of 2. So that's interesting. Finally, what we can also look at is just a last application of this is look at this performance scaling of quantum annealing in the adiabatic limit. So in the adiabatic limit, if there is no noise, the Landau-Zehner tunneling keeps you in the ground state. So the success probability in the limit of very weak noise is going to be 1 minus the escape rate, integrated escape rate. And what we do is we integrate that, and we get this amplification or this degradation of the ground state population from this noise amplification compared to a single qubit problem with ohmic spectral density. So just to conclude, so we've developed some new analytical methods with which we've been able to algebraically dissect frustration in 1+1 dimension, and we have been able to use this to calculate the scaling of incoherent tunneling at a spin glass bottleneck with frustration. And we've done this by basically this parity restoration technique, because in 1 dimension, frustration is simply a parity constraint. So just by moving an excitation, we are able to restore that. So for future work, what we would want to do is compute non-perturbative effects, such as renormalization of the gap, which would actually tell us whether we have speed up or not, and also look at the renormalization of low frequency noise, which is something that's also very interesting. We haven't looked at that yet. But just the main idea is we can see, here's another model which actually has 2 avoided crossings involving the ground state. So this is like an F squared model. You can play around with exact diagonalization. This model has 2 bottlenecks, and we believe that we are starting to build an analytical understanding of flux qubit noise in problems with frustration. Thank you.
Questions? Okay.
So what is the significance of this matrix element?
Yeah, so this matrix element is the basically the tunneling. It's a form factor. So if you look at the so if you write down Fermi's golden rule, you'll find that it's proportional to this M, this matrix element, times the spectral density. So this is basically computing the scaling of tunneling rates at a bottleneck. Yeah. Yeah.
More questions? You have still time for questions?
So the first thing that I see with this kind of frustrated loop is that you would have a floppy spin on the point of it, and then this kind of, when L and R are close together, this floppy spin would cause a perturbative anti-crossing.
Yeah, there is a crossing.
But that's not so. Is there another bottleneck that's competing with this, or is this the dominant bottleneck?
This is the dominant bottleneck. There is a second order phase transition. It's from quantum paramagnet to quantum ferromagnet. But this is after that. So that scales polynomially. This is an exponential.
Okay, so they don't happen at the same time.
No, they don't. They're separate.
Okay, thanks.
Thanks.